приглашу сейчас сюда подняться Эрика Chaissona, доктора философии, профессора астрофизики Гарвардского университета. Well, I can give you this mic.
Good, thank you.
Okay. And what about your presentation?
Let me forward it.
20 minutes. Yeah.
So it's not showing. Oh, it's coming here now.
Yeah. So your countdown, your presentation, your mic, and everything.
Okay. Доброе утро. Я немного понимаю по-русски. Я очень хорошо понимаю космос. I want to begin my talk today by sharing with you a story of something that happened to me in this city almost 25 years ago. I've been to Moscow many times, but mostly in the 1970s and 1980s, when this was a very different place. But I love the Russian people, I love the borscht, and I especially love the cold weather. But this time back in the 1980s, this must have been 1987 or 1988, I was at that time in Pushino, about 100 kilometers to the south. Never mind what I was doing in Pushino. It was one of those cities that was not even on the Soviet maps. But I received a telephone call from academician Keldysh here in Moscow. He asked me to come back to Moscow to spend a day visiting many of the labs and institutes and meeting some of the leading Soviet scientists. And so I took this as a great opportunity to indeed meet some of the scientists whose papers I had read for years and years. I think this was part of Gorbachev's program of glasnost, perestroika, at the time. So I was staying at the Akademskaya on Leninsky Prospect, and this great big man, he probably was from Lubyanka, came and picked me up and drove me around the city with great precision. And had an opportunity to meet people like Sagdiv and Sanyayev, Zeldovich, Ginsburg, Kardashev, Shklovsky, even just before he died, Sakharov. And so it was a real honor for me to meet these great Soviet scientists and who had written the papers that I had read as a student when I was in training at Harvard. But all during the day, as I went from laboratory to laboratory, from institute to institute, from office to office, I felt there was something missing. There was something wrong. And it wasn't until that evening when I came back to the Akademskaya, went across the street and walked in Gorky Park. Gorky Park, one of my favorite parks in all the world, that I realized what had been missing was that I hadn't seen any computers that day. There were no machines on the desks of the theorists. There were hardly any computers in the laboratories. And so the next day I came back to the Lebedev Institute, and I said to Professor Keldysh, where are the machines? Where are your computers? Where is the current technology? And so he looked at me very sternly, and he said, come with me. And he took me down a long, long corridor, hallway, to a locked closet. He unlocked the closet, opened the door, and there it was, one computer for approximately 100 leading scientists. And this was not even it was an 8088 chip in 1988. This was at a time at Harvard and MIT where we had computers, quite good, state-of-the-art computers on everyone's desk, in every laboratory. Computers that were linked together and networked for simulations and computation and for the control of other machines. And so, frankly, when I returned to Boston, I shared this information with my colleagues at Harvard, and I shared this information with my colleagues at MIT, where the missile defense system of the United States is designed. And I suggested to them, based on what I saw, that we probably had nothing in the West to fear because the Soviet system was not keeping up with the technology. it appeared, and I hope I'm not being disrespectful by saying that to anyone in the audience, that the system here was not embracing, was not welcoming machines, computers. And it is my own personal opinion that the events that took place 2 years later in this city in 1990 may have had something to do with the inability of that system to embrace technology currently. That will be part of my message today. We should not fear 2045 any more than we feared 1984 or the year 2000, or any more than we fear the end of the Mayan calendar this year in 2012. We should embrace machines. We should welcome them. And if we do it right, we will enter into a partnership, a symbiosis between humans and machines that will be to the benefit of everyone. So I am an atomic physicist by training, an astrophysicist by avocation now. And with my right hand, basically I research very specialized work in laboratories and at observatories, and then write up very specialized papers that are published in journals that frankly hardly anybody reads. But with my left hand, I try to take my work, and the work of other scientists mostly, and put it into a larger perspective, a worldview, a Gesellschaft, a Weltanschauung, a system that would enable me to understand better who I am and how all of the order and structure and complexity that I see around me has come to be. And that is what I, as a scientist, call cosmic evolution, and what some of the avant-garde humanists will call big history. It's presented here for you in this slide. The arrow of time. You've seen it before. From left to right, from the Big Bang to the current time. The arrow spanning in symbolic form, in graphical form, the entire 14 billion year history of the universe. Such that the kind of evolution we're most familiar with, biological evolution, neo-Darwinism, is one small subset, although a very important one, of a much grander scheme of change. Change writ large, we say. Change over all time and all space that enables us to understand how the galaxies, then the stars, the planets, and ourselves came to be. There's a lot of information contained within this slide. I'll just make certain that you see that definition in the upper left-hand segment of this screen. Cosmic evolution is a grand synthesis of developmental and generational change in the assembly and composition of radiation, matter, and life throughout the entire history of the universe. And I'll note that this is an opening slide of a massive website, a multimedia website, that is freely available to anyone. Just Google cosmic evolution. And in approximately 6 months, there will be an addition to this site where I will add an additional amount of material for scientists in an advanced track. Material that I've been working on, it seems, for about the last 100 years. So I am an empirical materialist, not a dialectical materialist, an empirical materialist. I seek to understand nature from a quantitative point of view. I'm a natural scientist. That's my calling. That's my language. I try to measure things. I try to quantify properties of systems. And I have the general impression that as we look out at nature and examine... Pardon?
Sorry. Some problem with interpreting. Just please wait for a minute.
I bet I'm talking.
Is it now better? Do you hear any interpreting? Yeah, okay, fantastic.
Is it that I'm speaking too fast? Usually in Italy when I speak
Probably
fast...
Probably you are in the future, and interpreting is present. That's
Pardon? Shall I go?
Yeah, please.
Right. So the point here I'm making is that I am an empirical materialist. I try to quantify systems. I try to understand ideas by testing them with measurements. And I'm plotting here, although it's not coming up on the plot and I'm not sure why not. I'm plotting here vertically. Not sure why it's missing. Whoop. Didn't want to go there either. Tricky device. I should be aiming this somewhere. Over here, degree of complexity. And over the course of time, I'm seeing generally different kinds of systems. I'm seeing in particular three kinds of systems: physical systems, biological systems, and cultural systems. And I'm trying to examine whether or not I can understand all of those different kinds of systems in the same manner. I've shown you here in iconic form, physical system. Here, a globular cluster, a large collection of stars on a huge scale. But for a biological system in the middle, I show a computer representation, a graphic, looking down along the axis of a DNA molecule, nanoscales. And then for a cultural system at the top right, I've shown a stained glass window in the great cathedral in Paris. Physical systems, biological systems, cultural systems, where I'm defining complexity in the orange, in the yellow bubble as a state of intricacy, complication, variety, or involvement, as in the interconnected parts of a system. I also see these same systems in the universe in many places, this being one of my favorite photographs, because it has contained within this one photograph all three of the systems that interest me. It has a star at the upper right. That's our star, the sun, a physical system. It has an astronaut, or cosmonaut, a biological system, and she is nearby her cultural system, which is the shuttle that brought her to space. All three of these systems, physical, biological, cultural systems, do have a common denominator, an underlying theme. And that theme, more than anything, I think, is the degree to which energy flows in these systems. If a star didn't have energy flowing through it, it would collapse. If the astronaut did not have energy flowing through her by eating, she would die. If the shuttle had no energy flowing through it, it wouldn't fly. Indeed, it's not going to fly anymore in the States. But I can, as a scientist, attempt to quantify each of these systems in the same way, just to show you briefly how a thermodynamicist like myself would do that. I would consider each of these systems, whether you're a physical, biological, or cultural system, as a box at the top that's open. It's open to the environment to allow energy to flow in. Energy in the top bubble flowing in. Waste, heat, Q flowing out. And you can show quantitatively, mathematically, that the degree of entropy decrease within the system is always, in fact, comparable to the degree of entropy increase in the environment. But the most cherished law in all of physics is the second law of thermodynamics, which suggests that the universe, on average, is breaking down, moving from complexity to simplicity. Yet within these systems, physical, biological, cultural systems, we see quite the opposite. These systems growing in complexity, from simplicity to complexity over the course of time. The beauty of this is that you can show that indeed the change in S of the environment is always greater for any of these systems than the change in S for the system, such that the second law is still preserved. None of these systems, including life, is a violation or even a circumvention of the second law of thermodynamics. They are all in accord with what physics, the most fundamental laws of physics, teach us. So here is how I try to interpret all of the data, the massive amounts of data I've accumulated over the years, by examining the flow of energy through systems. Like we call it free energy rate density. A little bit of a technical term, but it just measures quantitatively the amount of energy flowing through systems. And you can show in a definition, energy rate density, again, is a measure of the amount of energy available to do work or potentially to cause change flowing through a system per unit mass per unit time. And this is what the graph, the master graph, looks like by plotting logarithmically the degree of energy flowing through a system over the entire 14 billion years of time. It's a It's a system, it's a line that's coming up from whether it's galaxies like the Milky Way, through stars like the sun, through our planet Earth, on up through living systems, at the top right, cultural systems. And of course, at this meeting, we're all interested in what's happening right up there, the current time. Perhaps the opportunity to project this graph into the future. I'll tell you right now, evolution, in my view, is uncaring, unceasing, and unpredictable. We can see general trends in general, but very, very difficult to predict anything in detail. Nonetheless, I can show you what the mathematics are suggesting within the topmost part of that curve by plotting another graph, a log-log plot, fully logarithmic. On a fully logarithmic plot, an exponentially growing curve will be shown linearly. You see in the open circles, the dashed line, humankind in more recent years, over the last tens of thousands, hundreds of thousands of years, moving up along the curve at the very topmost portion of that red oval. And you see, by contrast, in the X's and the slightly dashed line, the machines, from the early machines of the industrial age through the jet aircraft of today. You say for a moment, wait a minute, are you saying that jet aircraft are smarter than we are? I have not introduced intelligence here. I'm speaking about complexity. And it may well be that a jet aircraft that flies under very fast computing control is more complicated than we are. We cannot, after all, fly, and we cannot compute as fast as the machine controlling that jet aircraft. That's all I'm saying. There's a lot of information contained within that graph, and you can see how the two lines are intersecting. And it may well mean that, yes, agreed, yes, again, machines are transcending humankind. But this is not necessarily to be a difficult singularity as much as an evolutionary milestone. The universal history has shown many, many cases of evolutionary milestones. Thousands of years ago, when the birth of language transcended symbolic communication. Millions of years ago, when land life transcended sea life at the Cambrian explosion. More than 1 billion years ago, when multicells transcended unicells. And way back to the origins of life, 3.5 billion years ago, when life itself transcended matter. All the way up and down the history of the universe, there are evolutionary milestones. You could call them singularities, in which case I would say to you, our single universe contains many singularities. And there's not necessarily anything special about this singularity that's about to occur as machines transcend humankind, other than it creates, perhaps for us, an existential crisis. So my suggestion to you would be that even though there are transcendent moments all through the history of the universe, the stars coexist with the galaxies, life coexists with matter, plants coexist with animals. Why cannot machines coexist with humans? Why can't we look upon this singularity event or grand evolutionary milestone in a positive sense and recognize that symbiosis is the interaction between two different systems in close physical association, real close to the machines, usually to the advantage of both, a mutually beneficial relationship. So these are my conclusions. 1, cosmic evolution is the grand synthesis of natural history. It aims to explain, to quantify, to unify the sciences, treating non-equilibrium, complex systems consistently and uniformly from Big Bang to humankind. 2, energy is a common universal currency in nature, all across the universe. Energy's specific quantitative metric, energy rate density, correlates with system complexity and may drive, at least in part, the process of evolution itself. 3, evolution is unpredictable, yet does display some tendencies. Evolution, as I said, is unceasing, uncaring, unpredictable, muddling path, meandering path. Yet it does show general future trends among physical, biological, and cultural systems, which are, including ourselves, nothing more than islands of complexity in a sea of great chaos. And fourth, machines are with us. They have arrived, here and now. The onset of smart machines represents an evolutionary milestone, not a technological singularity to be feared. Those civilizations that fail to embrace the machines symbiotically do so at their own peril. So that is my message, that the machines have arrived. We should welcome them. We should accept them. We should adapt to them. We should change and prosper. Спасибо.
Thank you so much, Professor.